Hey, me again. Last lesson, you guys looked at calculating change in using the equation delta H equals Q over N. All right, so we looked at heat energy being produced from a reaction using this equation and our mole equation that we've used before. Today, you guys are looking at another application where we are still talking about delta H, but it is a different way of calculating your delta H of a reaction. So remember, your enthalpy change of a reaction is just delta RH, R standing for reaction. Okay, and this formula is given to you, unlike last lesson's formula. So this is the formula that you are given. So it says that the change in enthalpy of reaction is equal to the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. And we are given a bunch of bond enthalpies. So you're always given the bond enthalpy values, otherwise you wouldn't know how to calculate it. And there are two types of questions that you can get. The first one would be like this, where I've given you all of the bond enthalpies for all of the bonds in the reaction, but you need to calculate the change in enthalpy of the reaction. And the other one, which we'll look at second, is you have to calculate the bond enthalpy of a bond, where you're given delta RH. And the second type of question is normally the one that they will be asking you, because it is a little bit harder because you have to do some algebra. And in the last 4 years, this is the one that has always been asked. But I'll still go through this because this is really important for understanding the process, and maybe if they're feeling nice, they'll give it to you. Okay, so normally in NCEA, they will actually give you all of the drawings of the reactants and products. So for example, they actually give you all of the structures drawn out, but they might not. So I've kind of put as a first step here to draw the structure of the reactants and products. So we've got CH4 plus, now I have two of these, so I've got two FCFs, and then I have a CH2 F2 and two HFs. So those are all of my bonds that I have. I can see all of them, I can count all of them. And essentially what we're going to do is you should always make a table. So I make a table like so. And on the left-hand side, I'm going to put what's on the left-hand side of my equation. So I'm looking at the bonds broken. So bonds broken. So that's my reactants. And then on the right, we're going to go bonds formed. Because in a chemical reaction, this is actually what is happening, is those bonds are being broken and then formed. So I get a highlighter. So if I'm looking at CH4, I can see that this bond is broken, this bond is broken, this bond is broken, and this bond is broken. Okay, that is 4 C to H bonds. So I'm going to go 4 times C to H. And then I know that there's 2 times F to F. So those are the bonds that are being broken. On the other side, oops. Okay, on the other side, I'm looking at bonds that are being formed. So I can see I've got 1, 2, oops, 2, still not doing it, there we go, 2 C to F bonds. I also have, do a different color, 2 C to H bonds being formed. And then I also have 2 H to F bonds. Right, so now I've made a list of all the bonds that are going to be broken and all the bonds that are going to be made. The next thing that I'm going to do is I'm actually just going to put the values in. So if I look at the C to H bonds, that is 414 joules. So 4 times 414, not joules, kilojoules per mole. And then over here, I've got 2 times 414. Looking at the F to F bond, I've got 158, so 2 times 158. And then C to F is 484. 484. And finally, the H to F is 565. And so what I am then going to do is I'm going to sum all of those up so that I'm left with the sum of the bonds broken and the sum of the bonds formed. So 4 times 414 plus 2 times 148, that's a total of 1972 kilojoules per mole formed. And then 2 times 484 plus 2 times 414 plus 2 times 565 is 2926 kilojoules per mole. So I've got my totals. Then I just need to do my equation. Delta RH equals 1972 minus 2926, 1972, which is negative 954 kilojoules per mole. Okay, which means that we have formed more bonds than we have broken, so we've released more energy, hence the negative delta RH, and we have an exothermic reaction. So this is the kind of simple version of the equation where you're just trying to find delta RH. Let's move on to the second type of calculation that you could get. Alright, so this is a question taken from the 2021 exam. As I said, in the past few years, they tend to give you the structural formula of the reaction. So I'm just going to scroll down to here. So this is what the question actually looks like. So this is also to do with methane, and it is the combustion of methane rather than it reacting with fluorine. Okay, so the first thing I'm going to do is, because they've given me the structure, I don't need to do that, but I want to make sure my ratio is correct. And so I can see in my balanced equation, I've actually got 2 of these, and I have got 2 of these. That is one of the most common mistakes, is when you don't have to draw it out yourself, you tend to forget your ratios, which will mean that you get the wrong answer. Now, in our case, we have been given our delta RH, and we're trying to find the average bond enthalpy, bond energy of the C to H bond in methane. Okay, so we don't have the C to H bond enthalpy in our table, but the process is exactly the same. So I'm going to go ahead and set up my table. Alright, we've got bonds broken, bonds formed. Alright, let's start with our reactants. So our bonds that are broken, I got 1, 2, 3, 4. 4 times C to H bonds. Okay. I then look at my equation and I have still got in my reactants 2O double bond O bond. So 2 times O double bond O. Okay, and then I've got CO2. So CO2 is C double bond O times 2. So 2 times C double bond O. And then I don't have another color, so I'll just go yellow again. Oh, we'll go green. Okay. Every water molecule has 2 O to H bonds, and I've got 2 water molecules. So that means I've got 4 O to H bonds. Not 2. That's one of the most common mistakes, is you'll recognize that there's 2 waters, but then you're like, okay, there's 2 O to H bonds. And then you go 2 O to H bonds. So you get the incorrect number. Right, let's substitute in my values now. You can kind of keep this as is, or some people like to make it x, like you do in algebra. So 4x is going to be our C to H bond. And then double bonded O's is 2 times 495. 2 times C double bond O's 805. And 4 times 463. Exactly the same thing. I'm going to total up my bonds broken and bonds formed. So on the left-hand side for bonds broken, 2 times 495, we are left with 4x plus 990. And on the bonds formed side, 2 times 805 plus 4 times 463 is 3,462. Using the equation that we're given plus the delta RH value, I'm going to make an algebraic equation. Let me just do this so I can, there we go. Right, so negative 802, because that was the delta RH value that I was given up here, equals 4x plus 90 minus 3462. Now, I suggest you always write it in brackets, because sometimes your unknown bond will be on this side. And so you've got to make sure that you have both of those being times by negative, so they're both minusing. So I always do brackets just to be safe. Then it's just a little bit of algebra. Okay, so I can go 3462 minus 3462 plus 990 is, so 802 equals 4x minus 2472. Do the same thing to both sides, which is adding 2472 to both sides. So negative 802 plus 2472 is positive 160 equals 4x. Divide both sides by 4, and I get x equals 417.5. Now, you cannot just leave it here if you have decided to substitute it in as x, okay? Especially because I don't have a unit on currently. So I'm going to say that the C to H bond is equal, round it to 3 sig fig, 418 kilojoules per mole. And remember, if you're not sure about the units, you can literally just look in the table. Alright, so that is your final answer. That's that. Hopefully a shorter video, and I'll see you guys next time.